welcome you all to the Gyan course on advanced topics on coding theory. I think it's my great pleasure to welcome Professor Daniel J. Costello. I think let's welcome him by that. It's his first time in India. He doesn't need any introduction. And but I just say one line. I mean, he's the co-author of the most popular book in coding theory, which is very widely used here as in India as a textbook for coding course. So let's welcome Professor.
Okay. The title is Advanced Topics in Coding Theory, and the whole class is divided into three parts. The first part is introductory. The second part is on low-density parity check codes, and that's an advanced topic. And then the last part, the last 3 days, is on polar codes, which is another advanced topic. So the part on polar codes will be given by Professor Emery Teletar from EPFL in Switzerland. He'll be here for the Shannon Day and then for the last three classes. The part on LDPC codes will be given by myself. That's the 3 days preceding the Shannon Day. And then the introductory part, the first 3 days here, there's a total of 12 hours of lecture, will be shared by Adrish and myself and another professor here from IIT Kanpur. So there's actually 18 hours of lectures on advanced topics and 12 hours in the beginning on basics. So we can't do everything in terms of the basic background in coding theory. In order to get to the advanced topics, we picked out some of the lectures based on lectures which Dr. Banerjee gives here at IIT Kanpur, which in turn were based on lectures that I used to give back at Notre Dame. And so those, we picked out some that we feel like lays the background for the later topics, which need to be the advanced topics which come later. But there will be some gaps, okay, and you can see that, and we'll try to fill them in with a little bit of explanation maybe if we get to certain topics that we didn't have time to cover the background on. So let me start with that introduction. So this first lecture is very general. There's a number of books. The book by Shu Lin and myself, it's a second edition. The first edition goes back to 1983. This is the second edition, which is twice as big as the first edition. And there's been a number of books written on coding. Some of the other well-known books are listed here also, in case you're interested in getting one of these for further study after you finish this particular class. And I should say too, I understand, I guess it's true that some of you are professors, some of you maybe are from industry, some of you are graduate students, things like this. I'm not sure, so the background maybe varies a lot among you. So the introductory material we have is, I think, fairly basic, but it assumes some things. You'll see this when I get into it. The advanced material will ratchet up quite a bit from the introductory material, but hopefully we'll have enough explanation in there that it'll be somewhat understandable. So these are just some of the things we'll talk about here during this first hour. There's three basic steps in any communication system. Encoding a message, transmitting it through a communication medium or what we call a channel, and then decoding once the message gets to its destination. So what's a channel? Well, these are a couple of examples. These are actually channel models. Okay, a channel is an actual physical transmission medium, but in order to do analysis of digital communications, and in particular coding, we need to abstract the actual physical channel to a model, and these are some of the popular models that are used in coding theory. One is a binary symmetric channel. So most of our digital communication is binary, so we would have inputs of either 0 or 1, and if we make so-called hard decisions, we'll say this a little bit more about this later, the output of the channel would also be either 0 or 1, and a transmitted 0 is received as a 0 with probability 1 minus epsilon, and is received in error erroneously as a 1 with probability epsilon. So epsilon is called something called the crossover probability or the channel error probability for a binary symmetric channel. So it's a parameter that describes this channel. So this particular simple channel model, but very practical channel model, because this is actually how a lot of digital communication systems are built, is described by the channel is described by a single parameter epsilon. Also, another is a binary erasure channel, in which we have, again, two possible inputs, but 3 possible outputs. A 0 can be received as a 0 with probability 1 minus delta, but it can be erased with probability delta. That just means when we receive the signal, a 0 is transmitted and we receive it, and we're not sure what it is. Okay, if we're sure we know what it is, we say it's a 0, or we estimate that that's what was transmitted. But if we're not sure, we put out an erasure symbol. This is a slightly generalized model from the binary symmetric model, which is also very useful in analyzing different kinds of communication systems. In particular, you often run into this channel in applications where, like network applications or internet applications, where you have what we're talking about here is mostly physical layer communication. Encoding, modulation, transmission, demodulation, decoding. But in many applications, there's higher layers of the communication system, and in particular, there may be additional codes which are used to check whether what went over the physical layer is correct or not. So this check can tell us, for example, what went through the physical layer has been received correctly or not. So if not, it would be considered an erasure. In this binary erasure channel model, an erasure could arrive because a higher level in the communication system says that whatever went over the physical channel was not reliable. So we consider it to be erased. So that is some idea of where channel models like this might come from. Now, Shannon started this whole business, Claude Shannon, back in 1948. You hear a lot more about him next Wednesday. Defined something called the channel capacity, which is simply a measure of the amount of information that can be conveyed reliably between the input X and the output Y of a channel. Basically said he proved the existence of channel coding schemes, okay, which achieve arbitrarily low error probability. So whatever you want, 10 to the minus 5 error rate, 10 to the minus 10 error rate, 10 to the minus 15 error rate. As long as the information can be transmitted across the channel at a rate less than the channel capacity C. So he was able to specify a capacity C, which depended basically on a couple of parameters of a channel, signal-to-noise ratio and bandwidth, which said that, all right, for a channel with capacity C, if you transmit at a rate less than that, you can receive the data at whatever reliability you would like, as low an error probability or as reliable a transmission as you like, if you do proper coding. So he proved that there exist coding schemes. So for example, we could say here, if a particular channel has a capacity of 2 gigabits, that means that we could transmit at rates less than any rate up to 2 gigabits with arbitrary reliability. I could get any reliability I would like if we do proper coding. But you could look at it as good or bad. He didn't specify how to define the codes. He just proved, it was a so-called existence proof in information theory. And actually, in this first set of lectures, the first 3 days, there'll be a couple of lectures on Saturday on information theory. He just said that proved the existence of codes, but he didn't show how to find them. And that was good in a way because it allowed researchers and engineers, it gave them a big field of study, okay, to keep us employed for all these years trying to find the best codes. So that's what I was fairly early, not among the earliest working in this field, but it's come a long ways since I started out, which the talk I give next Wednesday will indicate that to some extent. So the goal of coding theory is basically to design codes that come close to achieving Shannon capacity with reasonable implementation complexity. And that basically means that you don't want as you make your codes longer, basically you always can do better with longer codes. And as you make the codes longer, you don't want the implementation complexity to grow, say, exponentially or something like that. You want it to grow linearly, ideally, so with the length of the code. And so that's the basic goal of coding theory. So a channel code, what you wind up doing is adding redundant bits, which are sometimes called parity bits, to the actual message or source bits which you want to transmit. And these redundant bits are what facilitate the reliable communication. Otherwise, if errors are made during transmission, or we'll talk mainly about communication systems here, but we could as well talk about digital storage. I mean, the storage medium can be considered a channel. So all of the techniques that are applied to communication can also be applied to storage and vice versa. Although there are some differences in the storage medium and the channel that call for different types of codes. This is a hot area right now, as a matter of fact. But we'll focus, hot area for research. We'll focus talk more about the communication problem. So the idea, like if you think of that binary symmetric channel model, is that bits that were transmitted over the channel, there are errors made with a certain probability epsilon. So when you receive a sequence of bits, there are going to be some errors in it. How do you correct the errors? How do you find out where they were and change them? That's the idea of channel coding. Now what causes the errors? Well, the transmission medium, there's noise, there's always noise inherent in any receiver. So in transmission there's usually attenuation that takes place, and so you receive the bits with a certain signal, with a certain received signal to noise ratio. The noise being generated typically in the receiving equipment, in the electronics at the receiver, generates thermal noise, which gives you, depending on how much signal power you had, a certain signal to noise ratio at the receiver. There can also be in certain types of channels fading, a so-called fading phenomenon, which is like multipath for those of you that are involved in wireless systems. Or there could be interference, various kinds of interference that would take place during transmission. So lots of there are a variety of different causes of channel errors in transmission. In storage systems, it could be just defects in the storage medium, in the disk or in the tape, optical media now, dust particles, radiation, etc. These would cause bit errors if you just think in terms of this binary symmetric channel model that we talked about earlier. So the simplest possible channel is, or the simplest possible code is a repetition code. And a repetition code is just what it says. It repeats certain bits. So a rate 1/2 repetition code, if you want to send a 0, you repeat it twice. If you want to send a 1, you repeat it twice. So the first bit would be like the source bit or the message bit. The second bit would be like the parity bit. For rate 1/3, you could repeat a bit 3 times. I don't know, probably most of you are, so sometimes I call this the St. Matthew's code, because in the New Testament in the Bible, there's a phrase in the Gospel of St. Matthew that says, "But let your communication be yea, yea, or nay, nay, for whatever is more than these cometh of evil." Okay, so it was kind of a phrase indicating that communication should be simple, okay? But it's interesting that he didn't say, "Let your communication be yea or nay." He said, "Yea, yea, or nay, nay." So he was using a rate 1/2 repeat code, okay, so I credit him with the invention of the rate 1/2 repeat code about 19 centuries before Shannon. But what I take him to task for is, we'll see later, this particular code doesn't have the ability to correct any errors. Okay, if you receive 0, 1, so you transmit one of these two things and you receive 0, 1, you know that an error has been made, because you know the only two possible transmitted things were 0, 0 or 1, 1. But if you receive 0, 1, you don't know which of the two possibilities is more likely. So if you heard yea, nay in St. Matthew's time, you wouldn't know whether the person had said yea, yea, or nay, nay. But he should have said yea, 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 or nay, nay, nay. He should have used a rate 1/3 repeat code, because then if you have a single error, you say yea, yea, nay, yea. Well, two of the three things you heard were yea, so you can make the logical inference that what was actually transmitted would have been yea, 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 which represented a 0, rather than nay, 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 which represented a 1. So if you have enough redundant bits, you can not only detect the presence of errors, but you can actually correct them, at least with high probability. It could be that the channel made 2 errors, okay, but that's much less likely than the channel making a single error. If you want to think in terms of that binary symmetric channel model, the probability that there's a bit error on the channel, epsilon, is always less than 1/2. Okay, if you think of, if it was 1/2, you just get garbage at the output, okay, and you wouldn't have any idea what was sent. If it was greater than 1/2, you could reverse the two outputs, the labels, and you'd have a channel with probability, channel error probability less than 1/2. So this is something always less than 1/2. So correct transmissions are always more likely than incorrect transmissions. So guessing between two choices, whether the channel made more errors or fewer errors, the more likely thing is always fewer errors. And we'll talk more about this later. So this would just be an example of coding with a rate 1/2 repetition code, and maybe this was received where this 0 got changed to a 1. Call that a single error, or these two zeros got changed both to 1s. Or you could call that a double error. And here's an example, similar example, using a rate 1/3 repetition code. So this is the information sequence, the information bits, and these are the corresponding coded bits. And again, here we have a single error, and here we have a double error. Okay, and we'd like to be able to correct the most likely error patterns, which are the ones which, with the fewer number of errors, we'd like to get as many of those as we can corrected. So Solomon Golom, who was a famous information theorist, worked at the Jet Propulsion Lab in Pasadena, California for many years, passed away recently actually, made this comment. He used to write little limericks. A message of content and clarity has gotten to be quite a rarity. To combat the terror of serious error, use bits of appropriate parity. So he liked to write little things like that from time to time. Now we can model a communication system in this, generally in this fashion, where we have an information source and then a source encoder. And the information source could put out, I mean, it may put out information in digital form. It may be a continuous analog waveform or something. And then if it's analog, the source encoder would involve A to D converted to digital, and also to try to represent it in the most efficient form possible as a sequence of bits. And then sometimes, in some systems, you want encryption for security. And then the channel encoding is basically the addition of these parity bits or redundant bits to protect against errors. This is what we're going to focus on in this class, okay? There's some kind of modulation which prepares the bits then for, this is all kind of done from the source encoder output to the channel encoder output. It's all kind of in the binary domain. And then we have modulation, which converts to a waveform for transmission over the channel, demodulation, decoding, decryption, and then source decoding, which puts the information back in the original form for the intended user of the communication system. So source coding is designed to, really what you want to do is you don't want to send any more bits over the channel than you have to. Okay, you'd like to use the channel efficiently. So you try to represent the output of the source in a way which minimizes the number of bits required to represent it. Okay, so you don't want to send all kinds of extra bits which are not necessary because, for example, in a shared communication system, that would mean that other users aren't able to use the channel if you're wasting resources. So this whole process is known as source coding or data compression. If you've studied any of this kind of thing, the Lempel-Ziv algorithm or Huffman coding are two examples of this. Huffman coding when you know the statistics of the source, and the Lempel-Ziv algorithm when you don't know the statistics of the source. And then the output of the source encoder is referred to as the information sequence. We'll assume that to be binary. It doesn't have to be binary, but it's going to be some, the symbols are going to be from some finite alphabet, but binary is the most common case that we deal with in practice. And we want to make source bits, here I'm on to encryption. So we just want to make the transmission secure, so you can convert the source bits into a stream that looks like random bits using a method, using a technique called encryption. Examples are the data encryption standard or the RSA system or something like this. This is something that we won't spend any time on in this class. Now, our focus is going to be on channel coding to correct transmission errors introduced by the channel, as I mentioned earlier in the little example. So we introduce some redundant bits to the messages, and we do it in a controlled manner. Hopefully we're smart about how we do it. We want to correct transmission errors. We do it in such a way that we'll be able to correct transmission errors at the receiver. At least a certain number of transmission errors are the most likely transmission errors. And this whole process is known as error control coding, error correction coding, channel coding. It goes by a lot of, sometimes just coding theory. So we talked, the repetition code on one end is a very simple idea. Low density parity check codes, which we'll do the early part of next week, is more advanced. The sequence that comes out of the channel encoder is referred to as a code word, or sometimes we call it a code sequence. There are two types of codes, block codes and convolutional codes. And with block codes, we usually use the term code word. With convolutional codes, we often use the term code sequence. We'll see that a little bit later. So now what about modulation? Well, again, we're not going to say too much about modulation here. It's mapping code words into waveforms which are then transmitted over the channel. So again, if you studied any communication theory, things like phase shift keying or quadrature amplitude modulation are examples of modulation. Now, I'm going to say a little bit about this, a little bit more about that in a second here. The physical transmission medium, it may be wireless, in which case we get into problems. I mentioned fading typically occurs in wireless transmission, or wireline, where you typically don't get into issues with fading, but you have other kinds of noise or impairments of the transmitted signal. So again, the multipath would be in a wireless system, because the transmitted signal can be reflected off several different layers of the atmosphere, buildings, or whatever before it gets to the receiver, so you can have multiple versions of the transmitted signal that arrive at the receiver. So these are all messy things, and what coding theorists like to do is get rid of the messy things by abstracting and looking at the, models like the binary ratio channel or the binary symmetric channel, as we mentioned. Now, demodulation, and I'm going to say a little bit here in a second about how we get these channel models. So the function of demodulation, take this noisy received waveform and convert it to a sequence of bits, which in such a way that we try to estimate what the transmitted bits are. Now, hopefully most of the time we're going to get the bits correct. Sometimes we'll get them incorrect, and this is where that epsilon error probability on the binary symmetric channel comes in. So this is known as hard demodulation. If the receiver takes a waveform for each, and corresponding to each symbol produces an estimated bit, it's called hard demodulation or hard decision. And if the demodulator outputs are unquantized, so we don't have to do this at the receiver. We don't have to do hard demodulation. We could do something called soft demodulation. We could either leave the received symbols unquantized, or we could quantize but into more than 2 levels. Remember, the binary symmetric channel had only 2 levels, 0 and 1 possible outputs. And there's an advantage in terms of performance if you do soft demodulation, which I can indicate in a second. Now let's raise the thing here. Let me just, I want to indicate a little bit more about this, and I'll just use the blackboard. So typically, let's take, for example, again, we'll work in the binary domain, and let's say we're using PSK modulation, which means you can modulate your 2 bits. One of them is modulated with a PSK waveform with phase, say, 0 degrees, and the other modulation symbol is a PSK waveform pulse, okay, because each symbol is allotted a finite time interval, so you generate a sine wave pulse for each, corresponding to each symbol. And so you're going to transmit either a sine wave pulse with phase 0 or a sine wave pulse with phase 180 degrees. And if you shift a sine wave by 180 degrees, it's equivalent to changing its sign. So in terms of the envelope of the sine wave pulse, what you're transmitting really is either a +1 or a -1, okay, when you use binary PSK modulation. And I'm not going to go into the details of that particular process. It's just I want to show kind of a little bit where this binary symmetric channel model comes from. So, and let's just say for the sake of argument that we have a transmitter which generates a certain amount of power. So instead of saying we have +1 or -1, let's say we have +V or -V. So if we think of the x-axis here as representing voltage, okay, what we would transmit, say if we were going to transmit a 0, it would go out as a sine wave pulse of amplitude plus v, and if we were going to transmit a 1, it would go out as a sine wave pulse of amplitude minus v. Now what happens during transmission is there's noise added to that sine wave pulse. And then at the receiver you go through a matched filter. Okay? And at the end of the time period allotted to this pulse, you take a sample at the output of the matched filter. Okay? And that sample value basically is either one of these numbers, depending on what was transmitted, plus a noise value, which is a random variable. I mean, the noise can be modeled as a random process, so when you sample, you get a random variable. So what's received, okay, is basically it's either plus or minus v plus a noise variable n. Okay, and on most communication channels, n can be modeled pretty accurately as a normal, it's a random variable, it's a normal random variable or a Gaussian random variable. So you have what's received is a signal, which is a constant, plus a Gaussian random variable. So if you plotted the PDF, the probability density function of the received signal, if this was transmitted, the probability density function of the received signal would look like this, depending on how much noise power you had. The more noise power, the worse the noise was, this would be more spread out, and the less noise, it would be narrower. Okay, but you'd have, this would be your PDF of your received signal if a plus V was transmitted, and your PDF of your received signal if a minus V was transmitted would be like this. Okay. And what you do is you're going to, when you, at the end, after you go through the match filter and you take your sample, you're taking a sample of one of these two distributions. You don't know which one. Okay. Well, let's just say for the sake of, because you don't know which of these was actually sent. Say for the sake of argument that this is the distribution that you're sampling. Well, this probability, these are PDFs, so the area under the PDF is 1. And this, if your sample value is negative, your receiver is going to think that this was sent because what you sample is closer to minus V than it is to plus V. Okay, and this again is this idea that less noise is always more probable than more noise. So there's the most probable thing in this distribution is 0 noise, and then larger values of noise fall off according to the Gaussian distribution. So anything, the optimal detector, if you want, here we're getting into detection theory again, there are details but that I'm skipping over, would basically say anything negative received sample value at the output of the matched filter should be decided as a -1, which, or a binary 0, or binary 1, depending on how we map it. And any positive sample out of the matched filter should be decided as a plus V, which would be a binary 0. So that's how the demodulator makes this sequence of estimates. But it's going to be wrong with some probability. Otherwise, again, if the plus V was sent and we got a negative value, then the, and this, of course, this tails all the way out here, and we receive a negative value, then our estimate is going to be the wrong symbol. So that's going to be our channel crossover probability, our epsilon. The probability that a 0 was sent, but the demodulator estimates that a 1 was received. And that's exactly this area. So that's how you kind of, that's where that binary symmetric channel model comes from. okay, is it comes from this kind of statistical analysis based on the noise properties of the channel. So clearly, if these distributions, the noise power is larger, the variance is larger, then this is going to be a bigger area. Okay, we'll have a larger epsilon. And if the noise power is less, this is going to be narrower. You're going to have a smaller area, you're going to have a smaller epsilon. It also helps if the V is bigger. Okay, for fixed variance, if the V is bigger, we're going to have a smaller epsilon. If the V is smaller, we're going to have a bigger epsilon. So this is basically signal power, and the variance here is noise power. So the bigger the signal to noise ratio is, the smaller on the channel, the smaller the epsilon is going to be, and vice versa. But that's where that binary symmetric channel model comes from. Is there any question on this? Okay, a binary erasure channel, you'd simply say, okay, if I get anything maybe between here and here, since it's not so far from either one, I'm not sure. And I'd rather than take a guess which may be wrong, I'm going to call this an erasure. And then you could put more quantization levels in. Okay, you could put additional quantization levels in, which would kind of give you reliability information. If you got one of these, you'd be very confident that this was sent. If you got one of these quantization levels, you'd be less confident because it's more in the middle. And you can just leave, a lot of what we'll talk about later on assumes that we just leave R unquantized and deal with the unquantized value. Okay, which is easy to do in software. When you do it hardware, then you really have to quantize. But you can use a number of bits of quantization. You can use quite fine quantization and approximate the performance that you get by not quantizing at all. So I think from this little discussion, it's clear that the more quantization you do, you have more information about what was likely to have been sent. When you just do the hard quantization, you just have, okay, it was either this or this. But even with the erasure thing, you have a little bit of information. You know that, okay, it was too close to call, in a sense. And if you put a lot of different quantization levels in there, then the particular quantization level that your sample winds up in tells you kind of the reliability of the transmitted bit, that particular transmitted bit. So we'll talk about this a lot more later with low-density parity check codes in particular, is that the reliability of the received bits is what is used in the decoding algorithm, and that reliability comes from this kind of viewpoint. Okay. So to continue, that was a little break. So the channel decoding, if the we want to come up with an estimate of the information bits, and if they're not equal to the true information bits, then we just say that errors have occurred. And we can measure the error rate either in terms of bit error rate, which is the kind of fraction of information bits that are decoded incorrectly, or we can talk about the frame error rate, or what we for block codes it's more common to use the word block error rate. Frame error rate is a little more general, but it kind of is inclusive of convolutional codes. And that's just if you transmit sequence of blocks or frames, what fraction of the frames are received in error. And if there's any bit errors in a frame, that counts as a frame error. Frame has to be completely error-free in order to say that there's no frame error. Now, decryption, again, I won't say much about this. The key is key to decrypting. The source decoding, again, you take the original, you take your decoded information sequence and you try to invert the source encoding algorithm to get back to your original the form of your original message. Now, as I said, there are two kinds of codes. There's block codes, in which message blocks occur in binary sequences of length k, and these are mapped into code sequences or code words, usually terminology that's used for block codes of length n. And the encoding process is memoryless, otherwise each block of information bits is encoded into a code word, and then the next block of information bits, it doesn't remember anything from what happened before. The ratio k over n is known as the code rate. It's simply the fraction of bits which have to be transmitted over the channel which represent information bits. For bandwidth efficiency, you want to use high rates, which means you want most of your bits to be information bits, not have to use so many parity bits. But for error correction, you want to use lower rates, because the more parity bits you use, the more errors you can correct. So there's this trade-off between bandwidth efficiency and power efficiency, if you like, in terms of the code rate. So n minus k is the number of parity bits we add to a message in order to protect it against errors. Now, since there's k message bits, there's going to be 2 to the k. There's 2 to the k possible messages. These are binary. Okay, so we need to have 2 to the k code words. Now, we can consider non-binary. I mean, this could all be non-binary, and in certain types of situations, I mean, some storage applications can reasonably use non-binary codes, but most of the time we'll focus on binary codes because that's where most of the applications are. So this is an example of a little code. Say k is equal to 3. So there are 8 messages, 2 cubed or 8 messages. These are the 8 different possible sequences. And you have to assign if it's a rate 1/2 code or a rate 3/6, for example, then you assign code words of length 6, a code word of length 6 to each message. Now there are 2 to the 6th or 64 different possible 6-bit sequences. So choosing the code is a matter of selecting 8 out of the 64 possibilities. You want to do that in a good way. I mean, we won't say much about this morning. I think Audrey will get into it this afternoon, about how to do this. Now, another type of code is a convolutional code. Now, this is rather than processing the information kind of in blocks of block by block, it does the processing continuously. Now, okay, I'll explain what I mean here in a second. We also have an n-bit encoder output coming out of the convolutional encoder at any time with a k-bit input. But the n-bit output at a particular time depends not only on the k bits that came in at that time, like it would with a block code, but also on some number of previous input blocks, m in general, which is called the memory order of the encoder. So convolutional encoders, in contrast to block encoders, contain memory. And the convolutional encoder sequences can be of any length. They don't have a natural, fixed block length like a block code does. They can be of any length, so we call them sequences oftentimes, code sequences rather than code words. And there's 3 parameters that describe a convolutional code, n and k and then m. And, well, we had n and k for block codes too, but for convolutional codes, n and k are usually very small. Okay? For example, here, k equal 1 and n equal 2. Now, a k equal 1 and n equal 2 block code would be trivial. It would be like that repeat code. That'd be it. Okay? But here, there's memory in the encoder. Okay, this is a little shift register, feed forward shift register, and with 2 storage elements. And the encoding in this example, we have an input at each particular time L, and we have 2 outputs. And this output is the sum of the input bit and the one from 2 time units in the past. And this output is the sum of the input bit plus the previous one plus the 1 2 time units in the past. So this is a little rate 1/2 because there's 1 input bit and 2 output bits at each time. It's a rate 1/2 convolutional encoder. Decoding strategies. Okay, so we'll talk a lot more about this later. Actually, I should say, when we get to the part on convolutional LDPC codes, we'll see that there are cases where the N and K don't necessarily have to be small. They can be quite large also, but there's still memory in the encoding, unlike for block codes. The decoder wants to produce an estimate of the information sequence based on the receive sequence. I think we said that already. You can do that as well by trying to estimate the code word. And then if you estimate the code word correctly, you can just invert the encoding process and go back to the information bits. So it's usually easier to describe, you're trying to do the same thing, but it's easier to describe the decoding in terms of trying to estimate the code word. If you know the code word, you know the encoding rule, then you know the information sequence. So what is a decoding rule? Well, we have a receive sequence R. We have to, every possible R, we have to assign an estimate, V hat. So whatever we get, so again, you can think of this matched filter. If we have a block code of length n, you take n samples out of the matched filter and you get and you hard quantize, hard demodulation, you get a n-bit received word. Every possible n-bit received word has got to be assigned an estimated code word. Remember that there may be, in this little example, there are 64 possible binary sequences of length 6, but only 8 of them are code words. So you could think of a big table where you'd have the 64 different receive sequences listed, possible receive sequences, and next to each of them you'd put one of the 8 code words. And that would be your decoding rule. Now the question is, how do you do this assignment in such a way that what you really want to do is minimize the probability that you make an error? So, well, in order to do that, we have to have an expression for the probability of error. So the average probability of error, just the probability that our estimate V hat is not equal to V, can be written this way. This is the conditional probability of error given that we receive one of those sequences R. In our little example, there's 64 different sequences, possible receive sequences, times the probability that we receive that sequence. And we sum that over all R. So if you like, this is the joint probability that we receive R and we make an error. Summed over all R is the probability that we make an error. Now, the probability that given R, the probability that we make an error is simply the probability that the estimate that we have assigned to the receive sequence R is not the correct code word. So what we want to do is choose our estimate for every R. We want to choose the estimate such, so let's just say for a particular given R, we want to choose our estimate set that this conditional probability is minimized. And then we'll have the smallest thing possible in here, each term in the sum, which will minimize the error probability. Now, we can just agree that minimizing the probability that V hat is not equal to V is the same as maximizing the probability that V hat is equal to V. It just turns out to be a little easier to look at let's try to maximize the probability that our estimate is actually correct. That would maximize the probability of making a correct decision. We're either correct or we're in error. So maximizing one is minimizing the other one. Okay, so this conditional probability, P of V given R, can be written using Bayes' rule this way. Now, okay, so what's the problem with just doing this? Okay, I mean, what information do we have from our channel model? Well, our channel model doesn't tell us this conditional probability, but our channel model does tell us this conditional probability. The probability that we get a 0 when a 0 was transmitted, or we get a 1 when a 0 was transmitted, is either 1 minus epsilon or epsilon. So those epsilon and 1 minus epsilon are the probability of receiving a particular bit given that something was transmitted. So they're of the P of R given V variety. So if we use Bayes' rule to express this thing this way, we're now getting in terms here of something that we know, or at least we have a model for. And here we're still talking about sequences rather than individual bits, but we'll get to that in a second. So we want to compute this for every V. So it's given an R. We want to compute this for every code word, and we've seen that our channel model should help us with this term. And then we want to, whichever code word gives us the maximum of this, that's what we want to assign to that received sequence. Now, this maximizing this is going to be the same as maximizing the numerator, because the denominator doesn't depend on V. Otherwise, this is a little bit of a subtle point which can be confusing sometimes. We're not interested in the maximum value of this. We're interested in the V, the code word, which gives the maximum value. So we just want to step through this calculation for our 8 different code words and find out which one gives us the maximum value. It doesn't matter what that maximum value is. Okay? And since the denominator here doesn't depend on V, the only thing that matters is the V which maximizes the numerator, so we can boil it down to this. So this then becomes the maximum a posteriori probability a posteriori because it's after we've received the sequence. Decoder chooses V hat, whichever as the code word which maximizes this, okay, which would just be, we just have to look at the numerator here, P of R given V times P of V. So if we can compute this for every code word, then we can get our decoding rule which minimizes probability of error. Now, oftentimes, the code word probabilities themselves are all the same. If the message probabilities are all equally likely, then the code word probabilities are going to be equally likely. So these are all the same in many cases, which means we really only have to find the V which maximizes this. So that's what we say here, if the code words are equally likely. Now this is the typical case in a digital communication system. Where we run into decoders where we can't use this, and we'll see some examples of this later, when you have iterative decoding algorithms, where you go through several rounds of decoding. In the initial round of decoding, all the different code words may be equally likely, but once the decoder gains information through the iterations, then different code words have different probabilities. So in that case, in particular, you have to worry about the combined term, and you have to do map decoding. We'll talk about this with convolutional codes. Viterbi decoding, which is maximum likelihood, and BCGR decoding, which is map decoding. So a maximum likelihood decoder chooses the v hat such that this is maximized. This is just the one term here, this guy. Okay, now I've kind of indicated, yeah, it's somehow going to be related to this epsilon thing, but the binary symmetric channel, binary erasure channel, or if we leave it unquantized and we assume Gaussian noise, that's what we normally refer to as the additive white Gaussian noise channel. Those are all examples of memoryless channels. Otherwise, the noise itself is memoryless from symbol to symbol. It affects the symbols in a memoryless fashion as they come sequentially into the receiver. A case where this isn't true is oftentimes in wireless systems where you have fading and things like that. So these are channels with memory where this kind of assumption doesn't work. But in many cases, many real channels, they are at least approximately memoryless. And that means that this joint probability can be written as the product of the individual conditional probabilities. Joint conditional probability, product of the individual conditional probabilities. These are precisely your epsilons and 1 minus epsilons. Probability of receiving a particular bit given that another bit was transmitted. Now, again, a little just thing to make it a little easier to deal with. It kind of always like to avoid products if you can. If you take the log of this, you can replace the log of the product with the sum of the logs, so it becomes a sum rather than a product. It's an implementation thing. And since log is a monotone increasing function of x, maximizing p of r given v is equivalent to maximizing the log of p of r given v. Now again, remember, we're not interested in the actual maximum value. That would not be true if what I said would not be true if we were interested in the actual maximum value of this probability. The log changes it, okay? But we're only interested in the v, which maximizes this. And since this is monotone increasing, if a particular v maximizes this, it's also going to maximize this. So we can then take the log of this, which is the sum of these conditional probabilities. And each of these conditional probabilities is either an epsilon or 1 minus epsilon. So we're going to get a sum of either log epsilon or 1 minus epsilon, depending on what the received sequence is and what code word v we're comparing it to. So if we define something called, this is clearly going to depend on in n bits, we're going to have a certain number of epsilons, which is going to correspond to the number of positions in which what's received is different from what's transmitted. And we're going to have a certain number of 1 minus epsilons, log of these things, log of these probabilities, whenever the received bit agrees with the transmitted bit. Okay. So we're going to let this d of r and v, called the Hamming distance, we're going to let that be the number of positions in which r and v differ. Okay, those are the positions then for which this conditional probability will be epsilon. So there'll be exactly d times where we'll get the log of, we switch notation here from epsilon to p. Okay, p, this is just our epsilon, okay. The transition probability, crossover probability, binary symmetric channel, epsilon is used, p is used, okay. These are the common notations. So let's stick with p here since that's what I've written. So we're going to get log of p this many times, and the rest of the time, the block length is n minus this number, minus this number is the number of times we're going to get log of 1 minus p. So we have n times the log of 1 minus p minus d times the log of 1 minus p, and we can bring that second term in here. we have d times the log of p minus d times the log of 1 minus p, and we can write it this way. So this is what our metric becomes, if you like. Now remember what we're doing. We've got an r, and we're comparing it with all the different possible v's. Now, we look at this thing, and remember I said earlier that we can always assume that this transition probability is less than a half. If it's less than a half, then this ratio here is smaller than 1, which means the log is negative. This is just a constant. I mean, it doesn't depend on v. As we plug in different v, for a given r, as we plug in different v's, the only thing that's affected is this term, how many positions the two differ in. Whoops. Okay, this is just a constant, so minimizing this whole thing, or excuse me, maximizing, that's what we're trying to do, is maximize, just means we got to maximize this term. Well, this is negative. So we maximize this by making this as small as possible. Okay, which means for a given r, we want to pick the v hat as the code word. In our little example, there were 8 choices. So we go and compare r to each of our 8 code words and pick the code word which has the smallest distance to r, fewest number of errors. That's going to be the most likely. That's going to minimize this probability here. And therefore, that's the v that we should assign to that r. We do this for each of the 64 different r's, and we've got a maximum likelihood decoding rule. Is there any question on this? Okay, you know, I think I'm going to skip the last couple of slides here because we're running a little late. Let's, yeah.
Code word v has 5 bits.
Well, okay, but let's say 6. I mean, the example we're using is 6, yeah. Okay. Okay.
So 2 power 5 code words with possibilities. 2 power 5 code words possibilities. Total set. Right? Then you are selecting one which is in a way that the Hamming distance between receive vector and v is minimum.
Right.
Right? And in that 2 power 5 vectors, certainly you will have, v also you will have. I mean, where the distance becomes 0.
Yeah, well.
You will have a code word,
yeah.
Sur code word,
yeah,
and Hamming distance between this.
So your 64 code words, in the example we have, 64 different possible receive sequences. 8 of them will actually be code words. And then the v, which is closest to those, will be that code word. So in your list of 64, you'll have 8 where the distance is 0, and the estimated code word should be the receive sequence. So that just falls out of this, which is the logical thing to do. It's the other 56 where the r doesn't correspond to one of the code words that you have to decide which code word should you assign to that receive sequence, and that you want to follow this rule in order to minimize the error probability.